now for matrix multiplication. So to recap, we need two m by n matrices to compare and say whether or not they're equal. So in order to add, we need two m by n matrices, and then we can return an m by n matrix when we add up all the corresponding entries. We've also got scalar multiplication. So we take a real number and we take an m by n matrix, and how do we multiply those two objects together? Well, we just multiply each entry of the matrix by the real number r. So now we want to define a matrix multiplication, and here you need to be really careful about the sizes of the matrices. So here, when you multiply two matrices, the column of the first matrix, and order does matter, right? Matrix multiplication is not commutative, as we'll see. The columns of the first matrix, the number of columns of the first matrix, has to match the number of rows in the second matrix. So we're going to read in an m by p matrix, call it A, and read in a p by n matrix, call it B, and then we'd like to return an m by n matrix, right, so the p's kind of like cancel. We return an m by n matrix, call it AB, right, so A times B. So what should that mean? So here is a matrix A, and here is another matrix B. And so this matrix is an m by p matrix, so it's got m rows, so 1, 2, 3, blah, 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 m rows and p columns, 1, 2, blah, 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 up to p columns. And so if you take a typical ith row from the matrix A, what are its entries? It's AI1, because this is the ith row, and the first coordinate talks about the row. So AI1, AI2, blah, 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 AIP. So you know this is a row vector in RP. And then look at the column of B. So this is B1J, B2J, blah, 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 up to, right there are P rows. So the first coordinate counts the number of rows up to BPJ. And so this thing too is an element of RP. So we've got a row in A that lives in RP and a column in B that belongs to RP. So the sizes of these vectors match. So what you do is you take this row, twist it, make it match with the column, multiply the corresponding entries together, and then add all of that up. And what do? Take that result and put it in the ij entry of the product of this new matrix m by n. So you take the ith row, it's got p entries. The jth column, it's got p entries. Twist, match them up, add all the stuff together, and place that in the ij entry of the new matrix, the new m by n matrix, the product A times B. Let's look at a bunch of examples. All right, here's our first example of matrix multiplication. Here's how this works. I've got a 2 by 3 matrix and a 3 by 2 matrix. First question is, am I even allowed to multiply these two things together? Answer, yes, because the number of columns of the first matrix is equal to the number of rows of the second matrix. And again, order does matter. So we can't reverse the order of these two things. Well, yeah, we can. So this here you can reverse the order, but in general, you cannot reverse the order and have the definition still work out. So that's fine. How are you going to multiply these two things together? So I'm going to take row 1 and column 1, match up the corresponding entries, 1 times 2, 2 times -1, -1 times 1. Add them up, I get -1. Because I took row 1 and column 1, this thing goes in the 1, 1 entry of the new matrix. So there's that. Moving on, you take row 1 and now look at column 2. Twist, make them match up. So I get 1 times 1, 2 times 1, -1 times 1, add it all up, I get a 2. And so because I took row 1 and column 2, this thing goes in the 2, 1 entry of the new matrix. Right? Top row here still goes in the top row over here. So now that you've filled out the top row, and by the way, we should expect a 2 by 2 matrix in the end. So I know now to go to the next row. So I take the second row of the first matrix, twist, match it up with the first column. Second row, first column means this result goes in the 2, 1 entry. What is that result? Well, 0 times 2 plus 1 times negative 1 plus 1 times 1. So that's 0. So that's what goes in the 2, 1 entry. And then I take row 2 and column 2. That's going to go in the 2, 2 entry. And what is that? It's 0 times 1, 1 times 1 plus 1 times 1. Add it all up, you get 2. So that's what goes in the last entry. Let's look at a few more examples. It's very important that you understand how to multiply two matrices and whether or not you can even multiply them to begin with. All right, here's another example of here's another example of matrix multiplication. So this time we'll multiply a 3 by 2 and a 2 by 3. So I'm just going to take the two matrices from the last example and reverse the order because we can, actually, in this case. So a 3 by 2 times a 2 by 3, we should expect to get a 3 by 3 matrix in the end. And the number of rows of this thing needs to match the number of rows of this thing, and columns. Anyway. So the first thing I'm going to do is take row 1, twist it, and apply it to all 3 columns. So that's what's in this list of calculations. It's the row 2, 1 matched with 1, 0, and then matched with 2, 1, and then matched with negative 1, 1. So take 2, 1, multiply 2 times 1, 1 times 0, add it up, you get 2. 2, 1, 2 times 2, 1 times 1, add it up, you get 5. 2, 1, hit it on the last column, negative 2, and then 1, add them up, you get negative 1. So here is, because this is the first row of the first matrix, this thing is going to go in the first row of our product. So 2, 5, negative 1 goes in the first row. Now go to the second row, negative 1, 1. Twist, multiply, and add, and you get negative 1. Twist, multiply, add, you get negative 1. Twist, multiply, add, you get 2. So now here is the second row of the product matrix, negative 1, negative 1, 2. And then finally the third row, 1, 1. Twist, multiply, add, you get a 1. Twist, multiply, and add with the second column, you get a 3. And then finally twist, multiply, add, and you get a 0. So here is the last row of our product matrix. So this is a good final answer for the product of these two matrices. All right, probably a good idea to take a look at a non-example, right? So here are two matrices that you are not allowed to multiply together, and the reason is the number of columns of the first thing does not match the number of rows of the second thing. So here the product does not exist. But it does look like if we reverse the order, so for example, 1, 2, 0, 1, 1, negative 1, and write down 1, 2, 3, 4. Now it looks like here we've got a 3 by 2, and here we've got a 2 by 2, and so we should expect the result to be some matrix of size, right? So cancel the 2's, some matrix of size 3 by 2. It would be a good exercise for you to go through and try to multiply these out. So here you've got two matrices, A and B, right? So the product of A times B doesn't exist, but the product B times A, does exist. And then the size of that product is going to be a 3 by 2.